Hey everyone, welcome to this video. We are going to run an LSTM that will determine if a review is positive or negative. So to get started, please go to the course directory and download this lstm.ipynb file, upload it, and we will definitely need a GPU. With a GPU, this will take about 5 to 10 minutes to run. So go to runtime type, and here I've selected a T4 GPU. We will work with this data of reviews. So you will want to visit this link and you will need an account to download this data. So create an account, download it, and the data will be a zip file, which you will want to unzip and then upload it up here. It's going to be a CSV file. And once you've uploaded that CSV file, go to runtime and do run all. And again, make sure that you're using a GPU. Otherwise, this code will take forever to run. And let's go over what the code does. Here I do my imports. This code tells the model to use a GPU to speed things up. This is the review dataset we will work with. And let's see what it looks like. So it's a bunch of text reviews, and the sentiment can be positive or negative. Here I've created some custom code for importing the dataset. And once I run it, we can see that it has a length of 50,000. And yeah, positive or negative, and the text review itself. For the data set, which has 50,000, remember that earlier on in the course we talked about how we need a training data set, a test data set, and a validation data set, right? The training data set can be thought of as like the study material for a student. The test data set can be thought of as the final exam, and the validation data set can be thought of as the practice exam. So we'll split the data 50-50 for our training data set and our test data set. And for our validation data set, let's do a 90%, 10% split. Okay. Then we need to tokenize our text as we've gone over earlier on in the course. So I will import this tokenizer. And to see the tokenizer in action, for Kevin is great, it gets split into 4 tokens. Kevin is great. The last token is an exclamation mark. The tokenizer also allows us to turn these tokens into numbers, as we can see here, 4 tokens, 4 numbers. I've created a helper function that takes in a string, tokenizes it, and then turns those tokens into numbers, as we can see here. And I have another helper function, because remember that our model works with numbers, right? We can't just say positive or negative. We'll say positive is a number of 1, and negative is a number of 0. As we are working with batches, I have another function that makes some transformations to those batches. So here we use our helper function of string to list nums, as you can see from up here. We're going to pad the reviews so that they are all the same length. Turn the labels of positive, negative to 1 and 0. Unpadded lengths needed for PyTorch to ignore padding during training. And then this collate fn function returns 3 outputs: padded reviews batch, labels batch, unpad reviews lengths batch. We will still use mini batch stochastic gradient descent with a batch size of 64 for training, validation, and test data. And then just for fun, we're going to print out the number of training batches, which is 351. And let's create our LSTM model. I'll call it RNN here. We'll have an embedding layer, a LSTM layer, a linear layer, which we'll just call output layer, and a sigmoid output of 0 to 1, where 1 is positive and 0 is negative. For forward, we'll put the reviews through an embedding layer. And for embeddings packed, this is because, as mentioned before, unpadded lengths needed for PyTorch to ignore padding during training. we'll put the embeddings packed through our LSTM recurrent layer, and we return the cell state, the hidden state, and the hidden state's time steps. As I've mentioned earlier on in the course, even though an LSTM has a cell state and a hidden state, predictions are still made with the hidden state. So we'll take this hidden state here, pass it to our output layer, and then pass that current output to a sigmoid, again because sigmoid gives an output of 0 to 1, and we'll say 1 is positive, 0 is negative. Here I will print the model in case you want to sanity check things. So yes, embedding layer, LSTM layer, a linear layer, and a sigmoid output. For the loss, we will use a BCE loss and not cross entropy loss since we are doing binary classification, positive or negative. We'll use the atom optimizer and set a learning rate of 0.0001. We'll train for 5 epochs. I'll explain what this code does in just a bit. So yes, we train for 5 epochs. And during training, we will go through the training data, do a forward pass where we get the outputs, the loss, then back propagation, we compute the gradients, update weights to hopefully have better weights that give better predictions and better outputs, update gradients to 0 for start of next batch. And all of this code you see here is to calculate the training loss and the training accuracy during training, so we have a rough idea how well our model is doing during training. And all of this code from before up here is to help, well, calculate the training loss and training accuracy during training. Okay. Then, of course, we will go through the validation data right here to get, and then we get the outputs, the loss, and this is to get the validation loss and the validation accuracy during training. And this is helpful because we want to see how well our student is doing on practice exams during training. So during the 5 epochs, we see the training loss go from 0.66 decrease to 0.32, which is good. We want the lowest loss possible. The training accuracy goes from 59% to 87%. And let's skip validation loss for now. But validation accuracy increases from 72% to 83%. Now, even though our student has an 87% accuracy on what is like the study materials and 83% accuracy on like the practice exam, what ultimately matters is how well your student does on the final exam or final test given by the school. So what's the result of that final exam? We go through the test data set, and the final exam results are almost 84%. Awesome. It's not amazing, but remember that if we were just flipping a coin or our model was just guessing randomly, it would have a final test accuracy of 50%. So our model, while not perfect, has a better accuracy than just randomly guessing or flipping a coin here. I plot some graphs so we can see the training and validation loss during training, and the training accuracy and validation accuracy during training. And now, while it's nice to see an 84%-ish final test accuracy, let's actually test it out ourselves rather than just rely on this 84% number. So I've created a helper function, and I will give some example reviews to this helper function called predict review. And these example reviews I've created, I would hope, are pretty obviously positive or negative, right? I loved this movie. I want to see this amazing movie again. I hated this movie. I regret watching this movie. And now, our model correctly guesses that the first two are positive because it's higher than 0.5. And our model correctly guesses that the last two are negative reviews because they're lower than 0.5. I do wish the model was a bit more strongly opinionated. For here, I hate this movie. It says 0.46, so it's pretty close to zero point 0.5. Although the model still guesses correctly, it's a negative review. All right, that's it for this video. Thanks for watching.